Silicon Valley thought NVIDIA owned the future of artificial intelligence until Tesla secretly completed tape-out on the most powerful robotics chip on Earth. Leaked manufacturing purchase orders sent directly to TSMC and Samsung exposed Tesla bypassing traditional automotive suppliers entirely. While competitors were scrambling for server-grade GPUs, Elon Musk's engineering team quietly architected dedicated silicon built purely for physical AI deployment. Packing 5 times the usable compute and 9 times the memory bandwidth of AI4, the AI5 processor grants every Optimus unit local, real-time grok spatial intelligence with zero cloud latency. The semiconductor landscape just experienced a seismic shift and legacy chipmakers were caught completely flat-footed. The silicon dependency trap. For years, the entire artificial intelligence industry operated under a single, unchallenged assumption: to build cutting-edge neural networks, you had to pay the extortionate toll fees of legacy semiconductor giants. Tech giants and robotics startups alike lined up to buy general-purpose GPUs, spending tens of billions of dollars on server hardware that was never meant for mobile physical machines. These server chips were designed to sit in climate-controlled data centers, drawing thousands of watts of power while relying on massive water cooling loops. When applied to humanoid robotics or self-driving platforms, traditional GPUs hit a hard wall. They created severe thermal throttling, drained high-voltage battery packs in minutes, and forced developers to offload critical thinking to cloud servers. Cloud offloading created a dangerous flaw: latency. Relying on remote servers meant a robot had to send video frames over wireless networks, wait for a data center to process the data, and transmit instructions back. In dynamic real-world environments, or a vehicle must react to a sudden pedestrian or a robot must catch a slipping object. A fraction of a second of network delay is the difference between seamless operation and total disaster. Legacy chipmakers assumed that no individual automaker or robotics firm had the engineering capacity, capital, or silicon design expertise to build an in-house chip capable of running heavy vision language models locally. They believed Tesla would remain dependent on external hardware allocation for decades. But while legacy executives celebrated record GPU sales, Tesla was quietly assembling a world-class semiconductor team with a singular mission: build custom 2nm silicon optimized strictly for physical embodiment. And with official tape-out confirmed at both TSMC and Samsung foundry hubs, the monopoly of legacy chipmakers hasn't just been challenged, it has been completely shattered. The 2nm monster architecture. To comprehend why legacy chip executives are currently holding emergency board meetings, you have to look at the jaw-dropping architectural specs of the AI5 tape-out. While NVIDIA and Qualcomm concentrate on multi-purpose server architectures littered with legacy display controllers, Tesla stripped away every single wasted milligram of silicon logic. Engineered using advanced 2nm process nodes across both TSMC and Samsung foundries, the AI5 chip packs over 150 billion transistors onto a single ultradense die. It delivers a staggering 3,000 TOPS of native, localized compute power, representing a massive 5-fold leap over AI4, while cutting power consumption down to under 250 watts. Tesla solved the memory wall that plagues every other robotics startup by integrating 9 times the memory bandwidth of the previous generation. By stacking dynamic high-bandwidth memory directly adjacent to the custom neural processing units, data transfer bottlenecks completely vanish. Instead of waiting for distant cloud data centers, Optimus Gen 3 executes vision language action models in real-time spatial occupancy networks directly on the internal hardware. This allows the bot to process multi-camera visual feeds at 120 frames per second, making split-second physical decisions with absolute zero cloud latency. And then there is the multi-node fail-safe system. Tesla didn't just design one chip, they integrated a dual-socket, fully redundant AI5 board directly into the torso chassis of Optimus. If a dynamic task requires extreme spatial processing, like navigating a chaotic factory floor while carrying delicate components, both nodes link seamlessly to deliver instantaneous spatial reasoning. When you combine this raw hardware processing speed with direct on-device grok integration, the bot isn't just following commands, it is thinking, adapting, and reacting faster than the human nervous system. Real-world metrics and the 10 billion brain flywheel. When Wall Street analysts tried to model the infrastructure cost of running 10 billion physical AI brains, they declared the global energy grid would collapse under the compute load. But the leaked real-world testing metrics coming out of Giga Texas expose how fundamentally wrong those old-school projections were. Instead of burning tens of gigawatts on central data centers, Tesla turned every single Optimus bot into a self-sustained, independent power-efficient node. Running on a mere fraction of the power required by a standard household microwave, the AI5 processor executes full spatial reasoning local to the unit, slashing cloud data transmission costs to absolute zero during active operation. When you scale this 2-nanometer architecture across a global network, the macro numbers become staggering. A fleet of 10 million Optimus humanoids running AI5 silicon produces more localized inference capacity than every commercial server farm on Earth combined. Every individual robot operates as an active sensor node in a vast, decentralized intelligence network. When a single Optimus unit encounters a novel physical challenge, a unique door latch, an unfamiliar industrial tool, or slippery terrain, its local AI5 board instantly compresses the physical spatial coordinates and transmits the edge case telemetry back to Tesla's central Dojo superclusters. Within hours, Dojo retrains the global vision language action model, and an updated, hyper-optimized intelligence stack is pushed back out to every single bot on the planet via over-the-air updates. By owning the custom silicon, the physical chassis, and the decentralized neural network, Tesla has constructed an impenetrable, self-reinforcing hardware flywheel that makes legacy tech suppliers completely obsolete. The fabrication scaling and foundry dominance. The existential threat to traditional hardware suppliers isn't just that Tesla designed a superior 2-nanometer architecture, it's that they have built a dual-foundry supply chain engineered to manufacture this silicon by the tens of millions. While competing tech giants fight for limited allocations on third-party server lines, Tesla executed dual-sourcing tape-out agreements across both TSMC and Samsung's advanced 2-nanometer foundries. By securing dedicated wafer runs at Samsung's state-of-the-art Taylor, Texas facility alongside TSMC's advanced nodes, Tesla bypasses middleman markups and controls its physical silicon supply chain from top to bottom. By manufacturing these custom 2-nanometer boards in high-volume runs, Tesla drops the individual production build cost of the AI5 compute package down to a level that traditional chip vendors cannot touch. This vertical integration feeds directly into the mass assembly lines at Fremont and Gigafactory, Texas. While legacy industrial robots require external server racks costing upwards of $100,000, Tesla embeds 3,000 TOPS of localized AI processing power directly into an Optimus unit targeted at a sub-$20,000 total price point. Tesla isn't merely building a fast chip for internal testing. They are locking in the raw semiconductor infrastructure required to flood the global market with millions of fully autonomous humanoids every single year. The macro semiconductor monopoly. The tape-out of Tesla's 2-nanometer AI5 silicon doesn't just represent an engineering triumph, it marks the total collapse of the traditional semiconductor monopoly. For decades, Silicon Valley maintained a strict division of labor. Chip designers created the architecture, third-party foundries manufactured the silicon, and client companies bought expensive off-the-shelf processors to build their end products. By taking chip design completely in-house, securing direct wafer output from TSMC and Samsung, and embedding the hardware straight into mass-produced humanoid robots, Tesla has completely severed itself from the legacy hardware supply chain. Every single Optimus unit hitting factory floors or private residences acts as an active revenue-generating node in a global, decentralized neural computing network. Legacy chipmakers who built their fortunes selling general-purpose GPUs to centralized server farms now face an existential crisis. They aren't just losing market share in the robotics space, they are being completely bypassed by a vertically integrated giant that owns the compute, the physical chassis, and the data-gathering network. When 10 billion custom AI5 brains are active across the globe, processing real-world spatial environments locally, learning continuously, and communicating through Dojo superclusters, the cost of embodied physical intelligence drops toward zero. The race for AI supremacy is no longer happening in distant cloud data centers. It is happening right now in the physical world. Finally, when custom 2-nanometer robotics silicon makes cloud latency obsolete, the era of tethered, slow automation is officially over. The tape-out is complete, the foundries are spinning up production, and the decentralized neural fleet is about to take over. Will legacy semiconductor giants be able to adapt to Tesla's custom silicon takeover, or has the AI5 chip permanently sealed their fate? Drop your thoughts in the comments below.